right, I guess we can good to go. So let's see. How about we all just turn on your camera so that we can have a good photo for the workshop. All right, great. So nice to see you. Maybe still some of them are very shy. Let me catch this first. Oops. Oh, still. So all right, I guess we can start right now. And if you can feel free to turn off your camera for a moment. So I guess before we start the workshop, and we may need to talk about the EvoMass issue, because today I just upload a new version of the EvoMass. Let me share my screen first. Today I just upload maybe it's 25. I upload the new version of the EvoMass, the 0.21, and some of you maybe already successfully installed it on your server, but I guess some might be confront some difficulties. So if you try these two, this one and the backup one, if all not successful, you can still use the old version for this workshop. They just have not many things related to this workshop, so it's okay for the for using the old one. And all right, and because we just have 2 hours, so we will not have a ice breaking section, and I guess we can have the ice breaking in the Slack workspace after this today's section. And then let me to open my screen. So all right. So everyone can see my screen now, right?
Yes.
Yes, it's okay.
So let's start. So firstly, I want to talk about the schedule of this workshop. So this workshop will have a 5-day. The first day and the second day is about the technical tutorial and a small section lecture about the computational design optimization. And the second, then the third and the fourth day will have mostly is a design section that we will discuss based on the optimization result you get, and then we can see we try to use this optimization result in our in a design project. And then in the last day we will have a final presentation and a small review. I am trying to invite some experts from different to this review. So I hope that in the last day we can have some feedback from different perspectives. And the other thing is very important is that because the running the optimization maybe cost like hours, even 10 hours. So we cannot run the optimization during the section. So I would like to ask you to run the optimization after the section. And most optimization we will use just like sunlight hour or the solar irradiation, which is very fast. Even we run optimization with 1,000 or 2,000 iteration, it will just cost like 3 or 4 hours. So you can run the optimization during your sleep or during your lunch or dinner. So that's okay. And if you have more than one computer, that might be good. And because you can have more chance to try different options during the optimization. And for this workshop, we have I received 100 applicants in the first round, and then I select 29 of them, and then 21 of them accept this workshop. And in the second round selection, there still have 18 applicants, and then I select 5 of them. And then we officially have 26 participants, but I guess some might not become because maybe for the difficulty for their time zone, or they certainly have some things to do. And we have a participant from 10 countries and cover the 4 continents except for the Oceania, because I guess the time for them is a little bit too harsh. Before the lecture, I would like to introduce, give me myself a very short introduction. And I am now a postdoc researcher at Nanjing University. But when in my undergraduate and master program, I am still try to train myself as an architect. I just find that I already see the glass ceiling of this industry, so I try to find another way to make my contribution to the architecture industry. So I goes to pursue my PhD and to try to develop the EvoMass. But maybe like in the undergraduate and the master the program, I have participated in many architecture design projects. So this allowed me to understand how the architects works, and also need what they need during the design process. So this is very important when I develop the EvoMass. All right, now begins the lecture section of today, the lecture of today's section. And today we will have 2 sections. The first section is the lecture section. I will talk about some background about the computational design optimization, and as well as the theoretical background of the EvoMass. And then we will have a short break. And then we will go to the first technical tutorial about how to use the EvoMass. In this today's technical tutorial will focus on mostly on the building generation part, and then in the tomorrow's tutorial will be focused on the design optimization part. So the background. The reason why I developed the EvoMass is that we will now facing some challenge for the energy consumption and also the sustainable design. So in the background section, I will cover 3 major topics. The first one is the performance-based building design, and the second one is the computational design optimization, and the last one is the architecture design exploration. So for a moment, if we are in the architecture industry, when we talk about a high-performing building design, we are usually most of the issue or the technique is not about the architecture design. I usually have some like a high-performing material glazing and a mechanical system. It seems that those high-performing building design have nothing to do with our architects. But in fact, but we still know that many of the famous architects and or some famous building is actually have a characteristic with the very good building performance. For example, like the Swiss Re Tower in the London and the Frankfurt commercial building in the Germany. And actually, we can, based on this design, we can find that actually the architecture design can play a very active role in the sustainable design and also help the building to reduce its energy consumption. But the problem is how can we do that? If we are familiar with the sustainable design, we will know that like many architects like Ken Young and Norman Foster, but when we try to search for the early stage design for the low energy consumption or the building with some strategy like the nature ventilation or simulation, mostly we can find that those design is based on the empirical analysis. And then in the 1980s, and when the building performance simulation become more popular in the architecture industry, and some of the designer try to use some simulation like the energy pass or the CFD simulation to do some building performance simulation during the design process. However, when we use the building simulation, we will usually just find the problem of the architecture design or some drawback in your design that may cause some negative effect on the building performance. However, the building simulation cannot provide us the solution for the building performance challenge. So when we went to the 10 years ago, the computational design optimization become a new techniques in architecture design, along with the parametric design and the platform like the Grasshopper. And for the computational design optimization, it is based on the parametric modeling. So the first fundamental element for us to achieve the computational design optimization is the different kinds of the parametric design platform. And for the moment, the Grasshopper obviously is the most popular one, but we know still have some other platforms that can do the parametric design. And then the building simulation is also an integrated part of the computation design optimization, because we have to find a approach or technique to do the design evaluation. And then after we have the parametric model and the building simulation, we still need to have a technique to automatically search for the high performing design. So which is mostly we know is the evolutionary algorithm, but we also know there are many similar variants like direct search algorithm and also some algorithm based on the machine learning. But usually we will view all these kind of algorithm as the optimization algorithm. So these three elements also can be understood as a three very important aspect of the computational design optimization. Firstly, for the parametric design, the parametric model will define a design space for the optimization process to search for. And the building simulation will provide a method to help us to evaluate or assess the performance of the building design. And then we use the evolutionary algorithm to achieve the automatic design optimization. So just a very brief introduction of describe the workflow of the computational design optimization. Firstly, the designer have to convert his design concept or scheme into a parametric model, and then he will connect the the performance simulation with the parametric model, which after that the design generated by the parametric model will goes to the performance performance simulation part, and then the designer also have to define the design object, for example, like maximize the daylighting or minimize the solar exposure, and then to calculate the building performance as a performance indicator, or we usually in the context of the evolutionary design, we call this as the fitness score. And then the fitness score will goes to the evolutionary algorithm to let the algorithm know how well or how badly this design perform. And then the evolutionary algorithm will try to learn the relationship between different parameter and the design, and try to create a new parameter to the parametric model and generate a new design. And after usually 1,000 or 2,000 iteration of this circle, the evolutionary algorithm will produce a high-performing solution for the designer. However, the traditional computational design optimization usually suffer from the drawback of a very linear and close design process, and also when we try to use this technique, is also very laborious and time-consuming. And here is the diagram to show you what is the conventional or the regular design, the workflow when architects use the computational design optimization. Firstly, based on the design brief and the design condition, the architect have to come up with a design concept. For example, he maybe mostly when we try to have a better, for example, in here, we try to have a design with better daylighting, and then usually the architects may think that the courtyard or the atrium may be a promising solution, and then they try to convert this design concept into a parametric design, parametric model for the parametric modeling process. But usually this process is quite time consuming and challenging, because you have to usually cost 1 or 2 days to develop the parametric model, and also have to check whether this model will create some chaos design. And then you will use another 1 or 2 days to run the optimization process in this stage, and then get the result. However, because in most cases, the optimization result is usually what the design concept you put into the parametric model. So usually the optimization result cannot provide many useful information to the designer. So if we want to have a courtyard design, and then the optimization result just give me a courtyard design, so this cannot provide any extra information to help me to improve the design more, how to say, more radically. So in most cases, this information is not very useful for the architects. However, when we talk about the architecture design, the architecture design process is actually a design exploration process, or some researchers call this a design process combined with the divergent exploration and the convergent exploitation, which means that the designer usually try to explore different design alternatives and then try to converge into 1 or 2 promising design. And then they will, based on this promising solution, they will also have another iteration of exploration based on this promising design from the previous stage. And then they will try to have a iteration process to gradually comes to the final design solution. So if we want the computer to help the architects in their design exploration process, there have 2 questions we need to answer. The first one is that possible for a computer to independently generate the building design as diverse as architects does? And the second one is that it's possible for the computer to proactively explore different design possibilities as architects do. So this brings to the challenge of the current or the conventional computational design optimization paradigm, because we usually have to, these two questions can be more specifically described by the design differentiation in the parametric modeling and the design exploration in the computational design optimization process. And here is the two technical challenge I face when I develop the EvoMass. So for the design differentiation in the parametric modeling, usually in the real-world architecture design project, the designer try to create a design showing structural difference. However, if we take a look on the research paper focus on the computational design optimization, we will find that they are using very simple parametric model and create some quite similar design solution. So this solution can be understood that have a very low topological flexibility. And some researcher like John Harding also talk about this issue in one of his paper, and he said that usually when we use the parametric design tool like Grasshopper, because they have a strong logical dependency between different components, so the design will be gradually become inflexible during the design process. So he said that in summary, the parametric design tool seems unsuited for the early stage as they either lock the designer into one typology or require the laborious creation of many different definition, which means that definition means that the parametric models. And the second drawback of the current computational design optimization is the optimization algorithm. So the diagram on the left shows that the general design process based on the evolutionary algorithm or many other kinds of the optimization algorithm. The firstly will be start from some random sampling on the design space, and then they will use some some intelligent the evolutionary strategy to approach to the high performing solution in the design space. However, if we think about the architecture design scenario, usually we will have more than one good solution when we face a design problem. So it means that the design space may contain more than one global or more than one almost solution. So if we use the conventional optimization algorithm, usually the optimization result will only focus on one promising solution and discard other solution during the optimization process. So here is the second problem from the computational design optimization. So we come back to this diagram. So when we know that the challenge and the technical difficulty to achieve a very informative design optimization process, we can see that we use this conventional way of the computational design optimization. Usually, they cannot help us to overcome our design fixation and also have a strong causality, because the design you put into the parametric model usually is the design the optimization gives to you. So in other words, it's like the garbage in, garbage out paradigm for the most AI research. So after the background, I will talk about a little bit about the EvoMass. So the EvoMass is as the name, as the description in the football Rhino, is an agile performance-based building design optimization and exploration. And the EvoMass have two key components. The first one is for the building generation based on the generic design principle, and the second one is the diverse sky design optimization and exploration algorithm. And then I will show you some example based on the EvoMass. And so in general, the EvoMass have like this have 5 features. The first one is integrated and coding-free building machine design generation and optimization, which means that you don't need to have carry out any other programming when you use the EvoMass. So it makes you very flexible and also easy to use design tool when you conduct the performance-based design optimization. And the second feature is that the EvoMass have great reusability and capable of applying to various building machine design tasks and under different design conditions. This actually because the EvoMass is a generic design generation algorithm or the two keys. You can input different parameter to change the definition of the design, and then to make the design can be fit into different types of the design tasks. For example, you can use the EvoMass in a high-rise tower building. You can use it in maybe a middle-rise or the low-rise complex, the teaching or the commercial building. You can even use the EvoMass like in the building configuration design, like a kindergarten design. And the free feature is that the EvoMass is able to offer optimization with rich design diversity, and which is aimed to help the architect to extract and understand the performance implication. Instead of using the standard evolutionary algorithm, which usually just give you very similar solution, the EvoMass have algorithm that can provide diverse solution, which means that when you're comparing this design solution, you can find the similarity and the differences between this design, and which help you to understand which can help you more easily to understand the performance implication reflected by this design. And for the fourth feature is that the EvoMass is focusing on the design information gathering rather than providing a direct design solution. The reason why I tried develop the EvoMass is that usually the designer cannot create a design generative algorithm that can provide you a wide variety of design solution. But because the EvoMass only have 2 generic algorithms, which means that they cannot generate different types of the design like the curve or the freeform architecture. So rather than provide the designer a direct design solution, I try to develop the EvoMass that to provide the design information, and then based on this information, the designer can synthesize this information in their design process and help and also to provide them extra information to overcome the data poor situation in the early stage of the architecture design. And the last feature is that the EvoMass is also can help to facilitate the human-machine co-evolutionary design. For this point, because in some application of the EvoMass, the designer usually can be use the EvoMass for several design iteration, which means that the designer will firstly run an optimization, and then they find the problem or the issues of the in the optimization result, and then they try to come up with new design idea and run another round of the optimization. Which means that the EvoMass is like a machine designer accompanied with the human designer to explore different design space, focus on different design directions. So here is the, let me have. Here is the general design workflow when a designer uses the EvoMass. So the first thing is to start with the understand the design brief and the design condition, and then the designer no need to conceive a design concept or design solution at the beginning. They only need to define the constraint and the design objective for the EvoMass, and then they input this constraint and the design objective into the EvoMass, and then to let the EvoMass run the optimization. And the EvoMass usually can give you more than one solution. So based on this diverse solution in here, the designer can try to reformulate or redefine the constraint of their design problem and go back to this stage and run another round of the optimization. Or if the architect is satisfied with the solution, or they think that it is sufficiency for the design information extraction based on the maybe many iteration of design optimization, they can go to the next stage to develop the design concept based on the solution provided by the EvoMass. So the previous slides describe the general idea of the EvoMass. So from this slide, I will try to explain the mechanism of the EvoMass. So for the first thing is about the design generation. So for the design generation, I think it is easier for the architect to understand the implication from the design space. The design space means that when we develop a parametric model, it means that the parametric model can define a design space contain all the design variants can be generated by the parametric model, which is a design space. And if we use a very simple parametric model like this one, usually each of the parametric model only generate one type of the building. For example, the building with one courtyard in the center, or a building have a feature like the solar envelopes. So the design space actually is separate. It means that each design space only have one specific one family of the specific design solution. But there are also another possible method to construct a parametric model is a combinatory parametric model, which means that in one parametric model, they can have more than one generative algorithms to generate different types of the building. For example, one algorithm to generate the courtyard building, and the one to generate the solar envelope building, and one to generate some like a steel building. But however, for this type of the design, the design space, each of these small design space is actually just combined with each other, but have no overlapping relationship between each other, because you cannot generate a design simultaneously have the courtyard and the solar envelope, or the courtyard with the steel. So these two types of the parametric model will cause a problem. Is that when we try to search for this design space, each of this blue space correspond to one of these small space. When we try to just search the design solution in one of these small space, usually this space do not contain a high performance solution. And also, even they can contain a high performance solution, they usually only contain one type of the design. So for the other types of the design, they will be have in the other design space. So for the design optimization process, the process cannot extract to find all these promising solution in one design optimization process. So if we want to try to address this problem, we need to combine and also merge all these different design space into a large unified design space. So how can we do that, or how EvoMass can do that? The EvoMass using two generic form generation principle, which is the subtractive and additive form generation principle. Because these two principles did not describe any specific types of the building. For example, you cannot use the the subtractive principle to describe a design with a courtyard. So it means that it's not this mix. So the subtractive and the additive form generation principle have no relationship with have the relationship with many different types of the design strategy, but they have not to say that the courtyard is one of these types. So you can use the subtractive and the additive form generation principle to describe all kinds of the building, basically all kinds of the building in the world. So in reverse, we can use these two principles to generate these all kinds of the building that can be described by these two principles. Because these two principles have no direct relationship to any of the design strategy like the courtyard or the atrium, so they can generate whatever types of the building based on the performance objective, and then the designer can understand the architecture implication in the generated design based on these two principles. So for the technical point, for the technical point of view, the two algorithm is not very difficult. For the subtractive algorithm, just using the Boolean difference to create a design with the feature of the subtractive building volume, and the additive algorithm use the Boolean union to generate the building with the additive features. But based on these two generic form generation principle, I also add some other hard constraint in the algorithm. For example, alignment is a very important constraint in these two algorithms because when there are two small mass unit very close to each other, if we didn't do the alignment constraint, they usually will be a very narrow space between these two volume, and then this space usually useless for the architecture design. So the algorithm will detect these types of the problem and try to merge these two volume into one large volume. And then in some other cases, for example, when the volume is very close to the boundary of the building, they will also to directly break through the boundary of the building to become a large courtyard. And this three is for the subtractive algorithm, and for the additive algorithm, this is using the similar way. When the two additive units very close to each other, they will just merge into one. And then also when this additive unit very close to the boundary of the design, they will just to attach to the surface of the boundary to make the building have a more, I would say, to orderly building formal features. So when we compare the subtractive and the additive algorithm to the previous, the conventional parametric modeling approach, we can find that because these two strategies different describe any of these specific design solution, they actually implicitly merge all these small design space into one large design space, which means that all these design solution you can find the strategy from this design space. For example, you can find the steel, you can also find like the courtyard or the atriums, and also you can find some solar envelope if you see this example in tomorrow's slides. So come back to the design space, we can see that this is the one that based on the conventional parametric model, and now we use the additive or the subtractive algorithm to generate integrated design space, so that for the design optimization process, they can find different or many of the promising solution in one design optimization process, and to give back to the architects. So the other component for the EvoMass is the evolutionary algorithm called the SSIEA, which stands for the steady state island model evolutionary algorithm. And this algorithm is, let me see, okay, it didn't move. So this algorithm is improvement on the standard evolution algorithm, because the standard evolutionary algorithm is just like the conventional optimization algorithm will also converge into one region in the design space. But to overcome this drawback, I use the island model, which means that they will divide the design population into smaller design subpopulation and make each of the small design subpopulation to focus on different region in the design space. And then at the, when the design optimization process complete, the optimization result can provide all these good solutions from different regions. So it also can help to increase the design diversity and the differentiation in the optimization result. So tomorrow I will give you some example based on our like a mock design project. But in here I will give you some three very simple example I use I draw up during my PhD. And the first example is the solar energy optimization, which means that I try to increase the solar irradiation received by the building in the winter and try to reduce the solar irradiation received by the building in the summer, because we try to this example is based on the city I live in, is Nanjing, which have a very hot summer and a cold winter. So we use this objective to say that we can firstly to reduce the cooling load in the summer, and then to also to reduce the heating load in the winter. So when we run the optimization here, is also have a context. The urban context have a high-rise building in the southeast corner and have a three middle-rise building in the west and the north. And then I run the optimization and get the result from the SSIEA. I use 6 subpopulations, so I can get 6 LED design in the optimization result. And we can find that all of these solutions have a shared feature, is that they will have something like cell shading in the west part of the west-south surface of the building. And if we take a look on the context, we will understand that because the building is surrounded by different building in different directions. So only the south surface will have a receive intense solar irradiation in the summer. So the building, the optimization solution try to use the south shading to reduce the solar exposure of the building. However, here has a high-rise building which block much of the sunlight from the summer. So you can see that all of these the cell shading feature will be appear in the west part of the facade, the south-facing facade. And here, another thing is that when you use the EvoMass, I try to say that this is the design process, that when you see the design the optimization result, you will have some inspiration from the real-world architecture design, because you can see that this is all point to the design strategy of the cell shading, like this one and this one. And then based on this design knowledge, you can develop this concept based on your personal design preference. For example, if you want to have some more curvy or non-linear shape, you can transform this information or this design into more architecturally interesting building massing. And the second one is also the solar energy optimization, but I use another constraint condition for this design, which means that the boundary constraint is disabled, so that this space can be broken by the smaller the mass unit in the subtractive algorithm. And so when we compare this group of the design, we can find that all the boundary of the building will be broken, and then to form many like a vertical courtyards of the in the building. So if we understand the implication of this design, we will understand here has also have many real world example using the same design strategy to achieve also the same performance feature in their design. And the last one is I use daylighting optimization for the design, and then you can see that all those the broken boundary is missing, and then all the courtyard will be goes to the central and the northern part of the design, because when we try to maximize the daylighting, we need to enlarge the space between the target building and the building surrounded this building. So you can see that they try to make more space between this building and the building behind it, and then to allow more daylight to come to the north facing and the west facing facade of this building. And then similarly, you can also understand that you can find many similar solutions in the real world example, especially in Japan. They try to try to build some building in the very dense urban context, and try to also to have a better daylighting performance. So they usually try to make more space between each of the building. And then after you understand this implication, you can also develop this concept by introducing some other like a curvy or the nonlinear geometry into your design. So here to recap the whole design process based on the of using the EvoMass. So the architects first try to understand the design brief and the design condition, and try to formulate the design process and run the optimization and get the result, and then try to understand what is the performance implication in the optimization result, and try to develop this optimization try to develop this design based on the optimization result, or try to reformulate his design problem. And so here is another paper I want to share with you to also agree with the idea of when I developed the EvoMass, which means that surprisingly to us, both architects and engineers in our study say that the compute optimal was often used as the starting point for this exploration. So this is also the purpose of my development of the EvoMass, which try to use the EvoMass and the optimization design optimization process to provide the designer a starting point of their design, rather than to give the designer a direct solution for their design problem. So here is the end of the this lecture section. So we will take a look back on the schedule, and I think once you have a brief understanding of the background and also the EvoMass, I want to talk about what is the key point of the after section of this part. So for this workshop, I still want the participant can have a chance to experience the design process of using EvoMass in a small architecture design project. So based on the participant, I still not decide how to for example, to divide the participant into several groups or other kinds of format and then each group will prepare a design project and use this design project for the day 3 and the day 4 the design section. And so for a moment, I want to ask how many of the participants have time and the commitment to finish this design project, and then we will talk about it on the Slack workspace, and then we will try to figure out what is the format of the next two, the day 3 and the day 4. So here is the end of this section, and we can have like a 10-minute breaks, and we will come back in the maybe just 10 minutes later. All right. So anyone have any question about this section? Feel free to ask any question. My English just okay, so maybe something is not very clear.
No, thank you. That was very useful lecture. Thank you very much.
So, if
sorry, I have a question. Let me just turn off my video. Okay, can you hear my voice?
Yes, yes.
Okay, I see that you explain each one of them have a different, you divide the condition, climate condition like radiation of the sun or etc. And examine the project in a different section. If you want to examine all of those conditions in the building, that would be a little bit hard, or we had a strong computer to analyze them. Or
you mean
we should, okay.
Sorry, I didn't catch. You mean there have many different design objective, performance objective, and for example, the solar irradiation and the daylighting. How can we combine this?
Yeah, we want to combine this since each house can have several conditions that we want to consider in our project. We cannot separately analyze them. And
yeah.
if you,
I understand. You can continue if you still.
Yeah, that was all.
Firstly, I think that there is some application or previous application we try to combine different performance objective, like you said, the solar irradiation. So you can actually formulate these different performance objective into one fitness function. Usually, I will recommend you to use the single objective optimization, but you can also use the, like most of you maybe understand the multi-objective optimization. But usually, you run the multi-objective optimization. Usually, just give you too many solutions, and then you actually at the end you still to try to select the one have a best balance between different objectives. So for one thing, you can formulate a fitness function to combine all these objectives and then to run the optimization to get the result can achieve the best balance between different objectives. But actually, if you are going to, but in my point of view, what I want the architect to do is that you can run separate optimization, and then you can get separate design optimization result, and you synthesize this information by your own. For example, if you run the optimization based on the solar irradiation, you get the result like how to say the cell shading, right? And then you run the daylighting, you get the result like the building usually have a very shallow floor plan, and then you can synthesize this information because usually, for example, if your design not allow you to use the cell shading, you can still use the external shading device to replace this cell shading strategy in your building design. So what is the importance or the the purpose of using EvoMass is to how you extract the information you need, not the solution you want. The solution is decided by you, not the computer. So I think that the most important part is that this like a divide and conquer, or the computer do half of the job and then you still do your part of the job. And what is the most powerful ability of the human is the synthesize ability. We can synthesize no matter 1 or 2 or 3 or 5 objectives, and then we can synthesize. And this synthesize process usually is usually the source of our design ideation, and then you can think of some innovative design based on this synthesis process. So I try to encourage the user of EvoMass to try to understand the implication and then to do the design, not to use the solution directly from the optimization result.
So in this way, we want just to narrow it down to 5 or 3 group, and after that, we as an architect are gonna decide which one is the best for our project. Yeah.
You mean for this workshop?
No, in general, EvoMass. Not just in this workshop. The idea of EvoMass is to analyze different solutions and give us, for example, 10 or 5 best solutions for one condition or several conditions. And we as an architect, we're gonna decide which one is the best for our project in last 10 option that EvoMass give us.
Yeah, yes, you can understand that. And maybe tomorrow I will show you some previous example to usually cover the condition you just mentioned, and then maybe we can discuss your understanding of how to use EvoMass in tomorrow's section. So, is that still have any question about the EvoMass?
No, that was awesome. Thanks.
You're welcome. So if we don't have any further question, we can take a 10 minutes break.
Hey, I got one question.
Oh, all right.
Starting from my friend ended, is it possible to apply some simulations on one condition, like daylight simulation, and then start from ended, so I can apply another condition? Like I applied simulation on daylighting, is that fine? I got the final 10 results, yeah. And then from this, I can apply another condition, so I can reach them as the optimum solution. Is this possible?
Let me rephrase your problem. It means that when you run the first optimization based on one objective, and then you use the solution as the starting point to run another optimization.
Yeah, exactly.
Unfortunately, it can't, because it's to start over again to run another. But actually, there have another how to say possible approach is that, for example, you run a daylighting optimization, and then you not use the 10 best result, you use the 15 best result, and then usually you can run this on the CFD simulation, because this is very expensive. You can run optimization based on the CFD, which means that you will need to use like 10 days to finish optimization. But you can use this like a 15 solution to run the optimization based on the CFD, and to see how this 15 best solution for the daylighting can perform in some wind related performance, and then you select some of these. But technically, you cannot you cannot run optimization based on the current solution for another design objective. But maybe I can consider it in the future, because the design population is preserved in the optimization result, and then we can use this design population as the starting point for the next round of the design optimization. But this might be very challenging in the technical point.
Okay, perfect, thanks.
You're welcome. So any other questions? So if not, we will move on to our break section, and then we will come back 10 minutes later. All right. Okay, thanks. See you later. See you around. Hello. Hi. Can you hear me?
Yes. Okay.
Oh, I need to change to another computer. So this section we will focus on the application of the basic operation of EvoMass. And as I said, there are some might not be able to install the new version, so there may be just a very little bit difference between this one and the previous one, at least in the appearance. And but I guess it won't be a very big issue to understand what is the difference between this version and the previous version. But in the description, I will be cover some function that in the new version, but just a very little bit of that, and you can totally still use the old version for your design. So the EvoMass, when you install it, it will be on your Grasshopper toolbar, just like in here, and then they will have two different set of the component. The first set of component is the generative component, which will focus on, which is developed for generate the building mapping design. And then they'll have some tools, and some tools have not very useful for the design, but I will. But another tool is like this one is the automation algorithm, and then they will have another data recorder for the automation process, which can be quite useful if you run the automation. So we will first to start with the design generation part. So for the design generation part, sorry, we will firstly to introduce the additive full meshing component, and then we will talk about the subtractive one. And here have a tower one, which is not very useful. It's just based on one of my previous paper, and usually just generate a kind of the high-rise tower with sky garden and the atrium. So if you want to try this, you can check my previous paper, and I may not have time to talk about this component in this workshop. So for the first component, the adding meshing, so we can just click the setup here, and we will go back to this output items later. So the setback here, and when we come have this the user interface, and then we can firstly try to generate a random building, and we search first to disable this set target cost area and generate a design. And this is the design just generated by this component. Don't like the red. So I will go through all these parameter one by one, and then to let you know what is this function. First is the unit mesh number, which means that how many box will be shown in this design. So if you want to your building quite complex, you can increase this number, and then in the reverse vice versa, you can decrease this number to make your building more simple. For example, if you set to 3, the building is quite simple. And then you set to 9, the building can be very complex because they have many blocks to merge into together. And the second one is the filling factor. The first change to maybe like 5. Which means this filling factor means that how much of the building will occupy this virtual boundary of the buildable space. If you are setting a very low number, it means that the building will be very skinny, just like this. And then if you increase this number, the building will become fat. Fatter. But usually I am not this function is not very popular for the user, and the user may also use actual size constraint, which means that we can control each of these elements in their horizontal and vertical size. For example, if we set the 2424, means that each of this design will have a minimum range of 2 column grid size, and then the maximum is a 4 column grid size in the x direction. And if we set this is the vertical. Vertical means that each of the design box will have at least 2 floors, and then the maximum height is the 4 floor. And this is a horizontal size constraint, which means that how you constrain the actual size of in the x and y direction. So you can see if you set a very small number, the building can be very small because, all right, I guess we have to move to another one first, and we come back to this later. And another very important parameter in the additive algorithm is the column grid number, which defines that how large of the boundary of the buildable area space. The number here means that the number of the column grids in the x direction, and here is in the y direction, and also the floor number in the z direction. And if you, for example, you want to let's generate a random thing. For example, if you want to have a high-rise tower, usually have like a by A column grid in the floor plan, and then you have like a 30 floor level. And then let's see what's going on here. Yes, just like this one. This you can get a high-rise building with like maybe because the additive algorithm will not ensure that all the design will have a 30 floor. So usually you can generate another to see how large of the building is. And then if you want to create a building, for example, like middle rise deep plan design, you can just change this number to 10, and then you can increase this to number. So this set of the parameter is very important because it defines the initial boundary of the additive algorithm, which means that which related to the type of the building you try to create. For example, it's a slab type building, or a deep plan building, or a high-rise building. And then you can also define the floor height and the column spacing. And in the new version, you can define the column spacing in 2 directions, but in the old version, you can only use one unique value to define the column spacing. And then in the new version, you can also set this floor number with a different number, which means that the design can be changed in their actual height. All right, we come back to this. And if we using the actual size constraint, so each of the box will be subject to this constraint. And if you want to make this building more like for example, factor, you have to change this value. If it's 15 by 15, you can go to like a 12 by 8, and then you can get a very different deep floor plan design. And also you can increase the vertical size constraint to like a or 6. And then you can get a very fat design, fat building messing. But you can enlarge the difference of these two values and both of these two values to increase the diversity in the design. For example, if you make this very small and that very large, and you can get some more interesting design. Oh, sorry, this is the vertical. So if we change this like to a 4, so you can get some very narrow plan design. But still, the building can have a very different design, because when there are maybe two boxes merged together in this area, so they can still create a very large floor plan in this area. And let's move to the other parameter, is the exterior facade height. The exterior facade height is the EvoMass can generate the building facade for you, because in many cases you have to connect it to the simulation tool, because the simulation tool usually require you to define which part is transparent and which part is opaque. So the EvoMass defines several very simple facade scheme here for you. For example, here is the glazed wall, so which means that you can see that this very narrow strip is actually the wall, and then the below this wall is actually all of it is the like you can understand as a glazing wall. And then you can change to the like a straight opening, and then you can see they will have a wall in the above in each floor, and also have a wall below the opening. And in the new version, I also developed two new building facade scheme to help this model can be more easily connected to the honeybeam simulation, because the honeybeam simulation not allow you to use this kind of the geometry that to define the opening. The honeybeam require you to define the opening on a box. So all of this opening should be within the boundary of the surface. So in the new version, you can see that here they can generate some very boring rectangle windows for you. And then you can also change the number of subdivision to make the buildings more narrow or more or wider. And also they can still have the glazed wall. The glazed wall have only one difference, is that they will leave the wall between the two column space. We can assume that this is the space for the structural column, and then they will have a very narrow surface below them to allow the facade this surface to be connected to the honeybeam. All right, but I guess for this workshop, most of us will run the solar irradiation and the sunlight hours. So because the annual daylighting is very time consuming. So I guess for the facade scheme part, not many of you will need to use this function. And the generation. So let's go to the generate core. It means that in some cases, if you want to have the like a structural or the circulation core in your building, the algorithm can generate a core for you. But this core is actually subject to the fire regulation in China. So this function is not very useful for the people outside China. So I guess I don't need to explain too much about this function. So I just disable it. And then the EvoMass have a function to help you to create a building close to the target area you define. For example, this building have a build area like 19,000 square meter, and then if you set the test cost area, you can say like 25,000. And then the algorithm will try to search for a solution as close as to this target value. So you can see that here it goes to the like 24,000 square meter, which is very close to this to the target area. But if you set a very the gap between the generated design and the target area is too large, the algorithm cannot handle this. For example, if you try to add one here, the algorithm cannot handle this. Or maybe this is too long. Yeah. Oh, shit. Oh, come on. This is just an accident. So just keep in mind that you don't need to set your target area too much difference from the design you can generate. And we just disable this. But when you use this function, the algorithm will need to use extra time to compute the geometry to make the design close to the target area. So especially when the target area is very different from the design generator, so the computing time will be enlarged by this factor. So try to use a reasonable target area when you use EvoMass to reduce the computing time for the design generation. So here we have the advanced setting for the generation part. So the generation part, does the attractive interfering point is actually I seldomly will use this function because I just don't not sure how effective this can change the design. For example, the interfering point is just like the the interfering curve in the grasshopper modeling. That usually you have a curve here, and then something will be attractive or distracted by this curve. And this is the same logic. If you set the point here, and then the building will become closer to this thing, and then if you want the force between it, increase the force between it, you can increase this number. And also you can expel the building by set this to a negative, just like this. And here also allow you to set the factor in the horizontal and the vertical direction. For example, if you want to first you making very close to the design, and then if you don't want the building close to the point in the vertical direction, you can also try to give this negative value. Yes, just like that. So, but I still personally, I just don't very like this function, but you can use it in your design. I clear the point, and then each of the operation you make, you have to click the set parameter to make the building to reset to a correct position. And then here have a separation control, which means that when we try to use the additive function, usually we will find that we sometimes we want those small box to separate or more close to each other. If you want those small box separate from each other, you can use this function. And this function also allow you to define how separate the direction for the separation. For example, you can only need the design to be separate in the horizontal direction or the vertical direction, and in both directions. So you can see that when you use the separation control, you can find all these boxes will be detached from each other. But it cannot ensure that in all the cases it can achieve a very clear detachment, because sometimes if the box is very big, they will still
connect to each other. But you can see that, for example, like this one, if you disable the separation control, this thing maybe will be merged together. Yes, just like that. And also you can set this in the vertical direction. Since nothing happened. I guess this is like an example of the separation in the vertical direction. Each of the design will be very like a clear cut in the vertical direction. If you turn this off, and this will be a little bit merged into. We need to try to create the floor number to make this more obvious. Let's see, for example, like this one, if we use the vertical separation, what happened? It's a little bit difficult for the thing to, but in some cases, in the high-rise building, this may be more obvious or more stand out than in the middle-rise building. And the last one is you can make the separation in both directions. So this is the this part of the function. So we will make it back to the normal. And the next part is the open ground floor. This actually also not very useful function, but just required by some user, because in some cases the user want the building can be totally overhanging in the ground, so you can set this thing to make the building just flow in the sky, flow in the air. And you can also to for example, if you generate a high-rise building, all right, and if you, for example, have a high-rise building here, and you can set open floor. For example, you want to have like a sky garden in this area, you can use this parameter to generate the building with some floor you define. And excuse me for like 10 minutes, no, 1 minute. I need to provide some activation code to one of our participants. So, sorry. Where are you? Okay. All right, we continue, and we disable this. And this free function, you don't need to worry about them. They're just doing some basic check. And if you really want to know what it is, you can just to disable them to see what is the change in the design. And we need to go back to maybe a normal kind of building. And the next two set of the operation is the cutting boundary and the adding boundary. The cutting boundary allow you to set a user-defined boundary of the building, but I will show you how to do it. So just like here, you can draw a line here, and then you set the boundary here and set the parameter, and all the building will be within the boundary. But I admit that this function is not very good because nobody wants this like the exact shape boundary of the building. So I'm also thinking to upgrade this function to make the building have a more like the clear cut boundary of the design. And so we just clear the boundary. And the adding boundary is allow you to define a space will be always there. For example, if you look at this, if you think this is the podium of a high-rise tower, so you may need to set a statistical volume for the tower. So you can just you can define a volume here, and then you can define the volume here and set the boundary. So they will help, the algorithm will create a boundary, a tower in this boundary to act as to complete your own design. And the acting boundary also have another very useful function, is that if we have a building want to, for example, let me show here. I guess the YouTube will record the whole meeting. So if you miss any of the operation, we can still check back the YouTube recording, I guess, but I'm still not sure. Let's see. All right, if we have something crazy like this, but actually it can still be very useful for your design, I will show you an example. And if you move this thing in the top view here, all right, and we set this into our boundary set. And you can create some kind of design like this. And I guess some of you maybe see this kind of the high-rise building have some like overhanging structure in the building. So you can use this function to create this type of design. So it's just a very interesting application of this function I discovered. Sorry, I need to keep another application code. Who asked me about another one? Oh, sorry, another one. In the general section. And anyone who run low of the number of the run, you can use the activation code I just post in the Slack workspace. This is the general code that you can use within 5 days. All right, let's move on, and then we can clear the boundary. And here is the end of this part. And we will go back to normal design. All right, the last function is that you can create a fixed void, which means that this is actually a very early stage implementation of the operation in these two algorithms, because sometimes I want the building have like an L shape or the U shape floor plan, so I need to define a space that the building cannot go into it. So for example, in this design, you can click here, you will define a starting point. If it's a the number of the in here is means that the column grid number. If a 00 is means that in this, and if we have 1, it will have start from here the first column grid, and then the in the x direction, and the 0 column grid in the y direction. So we will, and the void size is means how large of the void you want to create. For example, if a 3 by 3, it means that you will create a 3 by 3 void in here. And if you make this the starting point from the 1 by the 1 1, and then the thing will be become like the interior courtyard of the building. So you can also use this function to create a statistical courtyard or the atrium in your building design. So you can see the hole will be always there. Let me. And all right, this is the mostly of the additive algorithm, and another very useful function in the EvoMass is that you can actually save this parameter setup. Once you're saved, next time you can, for example, you save this setup anywhere. For example, I save it in my desktop, and then next time if you are, for example, your computer is broken down or something like a power failure, and you didn't save your graphical file, for example, and then you will need to restore your design work, and you can use this function. And for example, if we change to other kinds of the number, and we can load this setup file, and then they will go back to our original number of the parameter setup, and then to help you to save your solution. And another very useful function is that if you can use this function to collaborate with other teammate or the other designer. You don't need to transfer the whole grasshopper file to your partner. You just only need to transform this setup file to your partner. Then your partner can restore your design parameter using this setup file. And here have another function is that you can do a very fast sampling to create some design in the Rhino space, but I think it is not necessary to display this function in here. And I guess this is the end of the additive meshing editor solution, the components. And I may go to the subtractive one first, and then to come back to this parameter. So let's move this side. And here I will describe or introduce to the another component is the subtractive building meshing generation component. So let's just generate a random design first. And you can see that the geometric features of this design is very different from the previous one, and I found that many of the users didn't like this one, but actually the subtractive one is the first algorithm developed in the EvoMass, and the additive one is the second one. And I almost try not to develop the additive one because I just getting lazy when I doing my PhD. But actually, the subtractive one still have a very useful function, and most of my research is done using the subtractive components. So let's talk about the subtractive component. The subtractive component is a little bit different from the additive one. Is that they will have the two different types of the, I call it subtractor, which means that each of the volume subtracted here is created by one subtractor. So there are two types of subtractor. One is the vertical subtractor, which try to create the space or the volume of the courtyard or the atrium, and the second, the horizontal subtractor is try to create this kind of the space, something out of space, like the sky garden or some rooftop terrace. So if we make one of this to 0, if we make the horizontal to the 0, only the vertical one will be shown in the design. And you can create a design space only have the vertical hopes in the building massing. And on the other hand, if you lead a vertical subtractor to 0 and have only allow for the horizontal subtractor, you can get another type of the building, just like this one. All the part subtracted by the algorithm is in the vertical direction. And so we just go back to the normal setup. All right, still have some bug didn't find. Cool. And this column grid number is similar to the additive function, so I just go very fast on this part. You can just change the boundary of the design and also the floor number of the design. And so this set of the thing is similar, and this is also similar to the additive one, which is just in the reverse way that you can define the size constraint of each of the subtractor. For example, if you create a vertical size here, like to the 10 is not allowed, a maximum number, and then oops. They will create a very large hole, but this is not like a normal architecture. So you just be careful when you're using this set of the parameter. Usually I will more careful when I use the subtractive one, because this parameter is usually more easily to create an invalid solution. This one will change the size in the horizontal direction, and the facade type is similar to the additive algorithm, and the generic code is also similar, and the set target cross area is a little bit different. Let's see. Let's change to a little bit more simple solution. Nice. All right. So there will be two ways to create a building design using the subtractive one to have a close area to the target area. For example, here is the 10,000 square meter, and you can change the area by scaling the subtractor, which means that, for example, we will go to 10,000. So which means that if you use this function to generate a building, they will try to change the size of this subtracted part of the building to make the building close to the target area. So which means that the boundary of the design will remain stable. So you can see that the inner part will become larger. But if you try to using the change by scaling the initial massing, it means that the building itself will be changed. Just like you can see, the whole building is shrink. So personally, I am more recommend to use this function by scaling the subtractor, not scaling the initial massing, because you don't want the building suddenly become very fat and suddenly become very thin. Okay, we'll close this. And in the advanced, it's also very similar to the subtract additive one. So you can see the set the interfering point, which means that they will attract or expel this subtractive part in the building to the interfering point. And also you can set the cutting boundary and the adding boundary for the design. And here is another function that very similar to the one in the additive algorithm, that you can make a whole building flow in the air or cup some floor in the middle of the building. And here is also the similar one that you can create a fixed wall in the building in the corner, in one or two corner of the building. So I won't go to the detail of this part, and you can try to explore the operation by yourself. And so we can save some time for the next point for this section is how to connect it to the simulation software. So before we go to the simulation software, let's delete this one and make this visible. And we need to talk about what is the meaning of all this output. For example, firstly, the area is the how large of the design generated for the moment. Actually, you can see that we have a list with 3 numbers. The first number is the total area. The second number is the area without the core section, and the last one is the area for the building core. But you can only see the area have a number when you click this option. And you can see that here have a different number, and but usually you don't need to use this generate core function. So you just need to using the list item to get the first number out of the area output is enough. And then we will go this bit by bit. First of all is the curve is the boundary of all the building curve. You can use this curve to generate different types of the shape you want. If you want to like to have a flip curve, you can use this function like just like this. If you want to like a more curvy shape, usually I don't recommend it to do so. And the second one is the surface of the floor, and usually we will need it for the simulation part. And also have the roof surface. The algorithm will help you to extract all the roof surface from the design. And the external surface is all the external surface of the building, and the interior surface. You can see the description here is that the surface facing to the courtyard. So in most cases, in the additive algorithm, it won't be generate a design with additive interior surface, and usually for the subtractive one, they will have interior surface because they usually have many of the courtyard and the atrium. And the exterior wall means that the opaque part in the building facade. So if you change to this, you will see it more clearly. So you can see this is just the solid part of the facade, and then similarly, if we will, this is also the interior facade, because here has no courtyard or the atrium, so there will not be have an interior wall, and then it's a exterior opening, which is the transparent part of the facade of the building, and here is the interior opening, which is the facade facing towards the courtyard. And here is the core surface and the core wall, which means that you can only see it when you use activate the generate core function. And here is the intersect point, is how you to see where is your intersect point, interfere point. So because we don't have the interfere point, so they just output nothing. All right. So for the next part, I will talk about how to connect it to the simulation. But I guess we can just because we are running low of time, so we just using the example I posted in the Football Rhino. So if you go to the Football Rhino, you can see here. You can see I already upload many of the example here. For this example is for the new version of the EvoMass, and this is the example for the old version of the EvoMass. And both of the example is all based on the Ladybug 1.2.0. So if you are using different version of the Ladybug, you can just I guess you are very good at the Ladybug and the Honeybean. So I guess it is not very difficult for you to connect the components by yourself. But I will here just to give you one very simple example. Here is the how to use this example. How to use the example I post on the Football Rhino. So here is the exact same one I post on the Football Rhino. Here is the additive meshing component that generate the building, and then usually. This example is developed to calculate the sunlight hour, so we can just first to see what is the result looks like. So you can see the result just looks like how many sunlight hour in the winter solid state in Nanjing, and if the color goes yellow, it means that they have like a 10 hour of the solar exposure, and if the color goes cold, it means that the sunlight exposure will be decreased. And here is the build how this building will affect the surrounding building, and here also I developed this one to see how this building and the surrounding building will affect the surrounding urban area. And so once you understand what I'm talking, so I will see, I will let you know. So for this example, only the external surface will be needed. So you just need the roof surface, external facade surface, and in some cases, if there have a courtyard in the building, you will still need to connect the interior surface to the bread, and then this bread will goes to the context in both of the components. And also you can add to this surrounding building in this BREP, and also the surface to represent the ground of your building plot. And once you use this example, you only need to define an EPW file on your computer to let the geolocation of the building types. So you can select just one existing file on your computer. For example, in my computer, I still store the EPW in my old DWA component. So you can go to the some like I guess there is the website for you to search for the EPW file for your location. So here is the EPW file, and for the EPW file, you can search for it in the Google or in Baidu, and then you will find this weather data and the energy plus. And then you can, for example, search for Nanjing. And you can download this package and then to extract the EPW file and save in some place on your computer, and then to get onto your the Ladybug or Honeybee. And then this is basically the simulation part. And once you connect the simulation, you already connect the simulation part, you can try to generate some design to see how this design can be affect the whole surrounding area. Or also in some cases, you can also to, for example, you can also to change this to your own building. So now you can see the sunlight hour on your own building, and you can to generate some random sampling design to see what is the effect of the performance, how the performance change with the building change. Let's see. And I also want to show you a little bit about how to use the Climate Studio, because Climate Studio is very easy to use, and also try to encourage you to try to use Climate Studio if possible in this workshop. And here is the Climate Studio, and I already upload the installation file on the Slack workspace. And I am also not very familiar with this software, but this software is very easy to use, and I will show you how to use it. Firstly, you can click here for the CS workflow template. And then you can select one. For example, I am very interested in the daylight, so we can select one like the annual glare. And it will need some time to load all the solution here. And then actually you can just use this solution to connect to the EvoMass. So you don't need to establish your own workflow to do the simulation. When you use the Climate Studio, you can just using this function to create all the workflow you want. But the Climate Studio using the, I guess is the geometry unit is the 1 millimeter. So you need to scale up the design generated by the EvoMass. And so we can show you one example based on the Climate Studio. So here is the one that will need to run the glaring. So we need to use the how to say the opening section of the building and also the opaque section of the building. So in this case, we will need to use both the opening and the wall. So firstly, we will need to define the basically we need to scale up all these things all together. Raw surface, and this can be And we need to define the wall part, and also to connect, and also the opening part. And now we have the roof, the floor surface, the exterior wall, and the exterior opening. And the other very important thing for the glaring simulation is that we need to define the analyzed surface. So we usually need to use this facade to the floor facade to as the basis of the analyst surface. So for this one, we will need to move it in the Z direction. Usually, we will simulate the working surface on our usually the daily the table. So usually we will move this surface a little bit higher. Like in China, we usually use like the 0.75 meters. So here this facade will be as the simulation surface for the glaring simulation. And then you can see when we finish this one, and we try to see what is this. And the ceiling, you can disconnect it first. And this is also not necessary. And all of this is not necessary. This is the window. This is the floor. This is the wall. So in that case, we need to combine the roof and the floor together and to make it to as the floor. And also we need to extract the wall surface here and connect it to the here. So the last one is the opening. And you just need to connect the opening to here. And you finish your setting for the simulation. And even the Climate Studio is very fast in the simulation, but you still need to make this thing a little bit, how to say, not very accurate for the simulation, because for such a huge building, if you're using a very accurate simulation setting, they will cost a lot of time. So usually for the like a spacing of the sensing grid, usually you can set a very large number. In here is 0.6. Usually I can set to like 3 of, and we need to invisible this first. And then we also need to make this the samples, the number of the sample a little bit smaller. For example, like 1,000. And I guess we are good to go. So you can click the run. And if you have this component, it means that the Climate Studio may not be run properly. So if you can solve this problem by hide the pop-up. So let's see yours. To true. So you can click here and so the pop-up windows will not show up again, and then they will run in the back stage, but it may be cost some times to finish the simulation. We have to wait a little bit, and then I can have a green. All right, we see the result. Maybe have something wrong. Yes, there must. Oh, okay. I get it. Where is the? I didn't make the right connection for the simulation grid here, and we need to put the simulation grid here. Oh, sorry. Here. So here we can see the simulation grid just like this. If we want to become a smaller, you can set this to 2, or you can if you want it become larger and faster in the simulation, you can set to 5. And because we just show you an example, so we are using very inaccurate simulation setup. And then we click again to see how is the result going. Yes, it's still running. Usually we take like less than 1 minute. If you have a very powerful computer, it will be very fast. But my computer is quite old, so it will take a while. But if you have a very powerful computer and you want to try the daylighting simulation in this workshop, and I will really recommend you to try the Climate Studio. And usually the result based on the daylighting is quite interesting from the architectural point of view. And yeah, you will see that if you run the optimization. Come on. Pretty slow. Anyone have successfully run this optimization, this simulation in the Zoom? Oh, okay, finished. Very slow. Usually I use my desktop computer in my office, usually can finish it within 1 minute, but this is just a very weak laptop, so you know. All right, still very slow. But you have already see the result is quite still very fast, because if you use like a Honeybeam, usually it would take you like 5 minutes to finish also very inaccurate simulation based on the annual daylighting. So we need to move to the but when you use the Climate Studio, try to clean the sieve drive frequently, because he will occupy many of the space in your sieve drive. Okay, I guess I need to restart the Rhino. All right, we will go to the last part of this section. Is about how to run the optimization. I need to stop my rhino first. So come back to the example file I post on the for Rhino. So the last one, I will run optimization based on this example, and I will encourage you to also run the optimization using this example, or you can establish your own optimization framework to run an example tonight or tomorrow morning, and then we will use this result for the next section. So I can delete the optimization algorithm here. So when we establish this simulation workflow, and then the next part is to how to connect it to the optimization. So before we go to the optimization algorithm, we first need to calculate the fitness function. And if you already see my tutorial on the YouTube, you will see that usually I will make a soft constraint on the floor area, because usually the generation will still occasionally generate some crazy design that have cannot satisfy the functional requirement from the of the gross area. So you will need to set a gross area to ensure that all the design generated by this optimization can satisfy the need of your design project. So for example, we will set that this design is like 23,000. So we set here like 40,000. So I guess it's a little bit too big, and you may change to the 25. So usually we will use like this called a penalty function to punish the design that cannot have a close value to the target gross area. So here we'll come to the result that have if you want to minimize the performance indicator, for example, you want to minimize the solar irradiation value, you usually need to make this soft constraint or the penalty function value larger than 1, just like this here. You can see I use the absolute value between the target area and the actual area, and then to add 1 into this value. So you can see that because this one is very close to the target area, so the part below behind the 1 is very small, it's just 0.085563. But if you generate a design very difference from the target area, this value will become larger. So we can generate another one to see what's going on. So let's see, this one has 22,000. So the penalty function will become larger in here. So you can see they will go from the 1.08 to the 1.09. So you can use this penalty function to combine with your fitness indicator. In here, we will see that is the sunlight hour on the surface of the building. So here is the result of the Ladybug component. It will give you the sunlight hour value on each of the analyst points. So you can you just need to make a mass addition, or to do an average calculation on this value, and then you can make this as a performance indicator, and then you multiply this indicator with your penalty function, and you can actually, technically, this is called the fitness value. It's not the performance value, it's the fitness value for the evolutionary algorithm. And then the last step is that you draw the optimization algorithm here to your canvas. And then the first thing is to connect the evolutionary algorithm to the generative component, and then to connect this fitness to the the output component, and then you click the evolutionary algorithm component. You can see the first tab will show the input, the list of the input and the list of the output. The input means that how many parameter the evolutionary algorithm will be generated to in this component to this component to create the design. Because we take a look on this design, because this one using 7 additive mass, which means that each of the additive unit need to 6 parameter, which define the x, y, z for the 2 corner points. So which means that each of the box will have 6 parameters. So if you have a 6 box, it means that you will have 42 parameters. So if you click here, you can see that they will have the first one is a 0 and the last one is 41. And you can go to the output section and set the direction of the optimization. For example, this is the one that we try to maximize the sunlight hour in the winter. So if you want to minimize the performance objective, you can just click here and try to reverse the optimization direction for the optimization. And then you go to the second tab is the main control tab for the SSIEA. And here you will see some of the setup parameter, and each of the parameter will have a direct impact on the result of your optimization. So the first one is the number of subpopulation. If you remember the idea of the EvoMass, you will see. I will show you this image, and then you can see that this is the number of subpopulation. Means that if you have a 5 subpopulation, so the optimization process can focus on 5 different areas. But if you have a 3, it means that the optimization process can only focus on 3 areas. So if you want your optimization process more explorative, you can increase the number of the subpopulation. And if you want your optimization process more efficient, you can decrease the number of the subpopulation. And the next one is the size of the subpopulation. It means that each population, how many individuals in each of the subpopulation, and if the subpopulation is you increase this number, it means that the whole population will become larger. So it will make the optimization process a little bit slower, but it will cover more the design space because you have more individuals. Which means that they can sampling more design to visit different region of the whole design space. And this one is the generation. It means that how many iteration or generation you want the optimization will proceed. And the mutation rate. Mutation rate is a technical term for the evolutionary algorithm, which means that how many the random shuffling can be happen in each of the generation. And if you have a very high mutation rate, the optimization process will be much look like a random search. And if you have a very small mutation rate, it means that the design optimization process will be less explorative but become more exploitative. So, but usually you can just use the default setting. It's okay. And then it still have a mutation rate in decay. It means that if I want to say that if the mutation is 100%, it means that they can still generate a random number from the 0 to 1. But in the later part or the later stage of your design optimization, you want to shrink your random shuffling range, so you can gradually to make the radius of the search space smaller with this operation. And the last one and the next one is the migration rate. Migration rate means that because they have a different subpopulation, and in some cases one subpopulation may be goes to the conversion or stuck by a local element. So in that case, they can exchange some design with other subpopulation to help them to escape from the current local element. But usually this this option is not very I not very recommend you to use, because if one subpopulation have a very high performing solution, and then this subpopulation can exchange this high performing solution to other subpopulation, it will make the other subpopulation just like polluted by this one, and then become very similar to the original subpopulation. So it will make the two subpopulation have a very similar solution at the end of the optimization. So instead of use the default number, usually I just set this to maybe much smaller number, like 0.01. And the tolerance size, it means that each of the how many individuals will get evolved in each of the generation, because I use a steady state replacement strategy. You don't need to understand that, but just a technique to try to make the optimization process more efficient and more have a higher evolutionary pressure. So if you're just using the A is a little bit small, and usually just using 10 is okay. So when you change each of this parameter, this number will tell you how many design will be generated and evaluated for the whole design process. So you can, based on this number, to determine to predict how long the optimization process will be last for. For example, if like one design will use like 30 seconds to finish the simulation and the generation, it means that 1 minute you can generate 2 design, and 1 hour you can have 120 design. And if you have like a 225 design, you will need to have like 2 hours to finish the whole optimization process. And let's go back to the parameter. So for when you're running the officially try to run the optimization, here is usually I will recommend a set of parameter you use in the optimization, which is you can set the number of subpopulation to 5 and the size of subpopulation to 30 or 40 is okay, and the tolerance size to 10, and the tolerance selection rate is 0.5 is okay. And here usually I will take it to the 0.01, and I will make this as default, and then you can change the number of generation to decide how long of your optimization process. If you are running a very fast optimization, you just try to see whether the optimization work or how the design will be generated. You just try to generate to run the optimization. You can set a very low number. Usually you can set 30. You can see they will have 1050 iteration. And if you are, for example, in this workshop, you don't have too many time to run the optimization. I will recommend you, at least if you are for the final optimization and you want to get some correct result, you at least need to have like a 15 generation, which means that you run an optimization for 1,600. And if you have more time or your computer run very fast, you can go to 100, which means that you have a design optimization process for have 3,000 design generation and evaluation. But based on my own personal experience, I think that if you just run the like a sunlight hour or the solar irradiation, usually just can be finished in 5 seconds for one design. It means that even a 3,000 design iteration usually will cost you like 3 to 5 hours. So it is very reasonable. So you don't. So I will recommend you to run a little bit longer optimization process. And here I have to show you another very important thing here is that how the organization will be run. Let's start another example with. I will try to run an example organization without any simulation and to show you what's going on during the organization. So which we just established a very fast part of the very simple framework. You don't need to follow this this operation. I just want to show you something during the organization. So when you finish your when you finish your organization framework, you need to first. I will recommend you save the framework first in case something bad thing happened during the organization, and we will choose a folder to. All right. Here we have a folder to restore our organization framework, and let's see where is this. Where is this? And here has example. And the other thing I want to share with you is, let me see, is that usually we can also use this component to record something we want to. This component will help you, for example, like just ask the question that if I run organization combine many different indicator, is that possible for me to restore all this value during the organization? It's actually it can. So you can use this component to restore all the data during the organization other than the fitness value. So this one will, when you use this component, you have to save your GH file first, and then you right click here, you will generate the two paths directory to save the record data. And the second one is actually they will create a folder to make the screen catch during the optimization when they find a new improvement solution. But I found this screen catch is not very accurate, so you just leave it behind for the moment. And then, for example, in this small case, I want to record the floor number, the area number. So we pretend that we have other value we want to record, and then we maybe want to record the area of the floor surface and make a mass addition. Sorry. And we get the result. Here have 8,000 square meter of the floor surface, and then we put it here, and and we have a panel here to see the number, and we can see the number is here, and then we will need to another panel to let the component know which, and we can first connect these two value to the other, and then here have the two value. It means that you have to you need to let the component know what is the name of these two value. So for example, you will say that the first one is the gross area, and the second one is the roof area. And you click here and do the multi-line data, and then to connect to here, and then you can check your result here to see the gross area is this and the roof area is this, and also you can connect your fitness into the fitness. It's all right. And then you go back to here, you can see already have a XML file to record the data, and you can use a notepad or just using If you don't have the notepad, you can use like I don't know what is this notebook or something in the English version of the Windows, and then you can see here. You can see all the number is already recorded here. The course area is recorded. The roof area is recorded, and the fitness is also recorded. It also record the running index of design. But so before you run the optimization, when you click the run, you have to delete this file before you run the optimization, because they will add the original the number already recorded in this file. So if the file already have some data recorded in this file, they will add this data behind this or the previous one. So the running index may be not accurate. If you want the running index can be correspond to your optimization, the running index in your optimization process. So you need to delete this one first, and then you can also see the print screen folder is already here, and then he actually make a screen catch for the partial part. So before you run the optimization, you can safely to delete this one, and then last one is to run the optimization. Here I won't change anything. I just run a very fast one, have 165 design. And after the optimization process start, you will have some the design generated and evaluated in this list. And you can see that already have something recorded in this folder. And also this thing will be changed dynamically when each one will be generated. They will add a new entry for the recorded data. And we may need to let this to run a little bit to see the result. The computer is a little bit too slow. So after the first generation finish, the SSIEA will help you to save all the data and the GIF file here to help you to restore the GIF, your whole program if your design is collapsed or broken during the optimization process. But you need to wait to the first generation finish, and then the backup file will be automatically generated. And here we will have a 45 individual before we reach the second generation. So just wait a little bit. So you can see that when they finish the first generation, here will be automatically generate a backup file folder. And here you will have, I will talk about this tomorrow, but you can see that they will help you to even save your GIF file here. So you don't need to worry about you didn't save the GIF file, and because you have already been saved. And also the parameter setup file will also be saved in this folder. So just let you to be worry free during when you're using the EvoMass. All right, I guess this will be the end of today's section, and I will stop the organization here and stop the screen sharing. So is there any question about the second section of today's tutorial? And I'm run out of water. So I hope you can basically understand what I'm doing in this tutorial section, because our time is quite limited, so something is very fast. And but I guess the YouTube may be recorded, and I also recorded the second section here, and then I maybe post it on the YouTube, and you can replay this section after today's section. And for today's the task after the section, I will hope you can run the optimization by your own, and then tomorrow I will use the optimization you run to help you to understand the result of the optimization, and then we will have the second section to talk about how to apply the EvoMass in the design. And the very important thing is that you guys can be try to make a good after the section, and then to also try to find a project for the design section. And I recommend you to find a project have a medium, not very large, but not too small size. At least have a like a 5,000 or 20,000 square meters for the course area, and have like a 8 to 15 floor. Don't be too small. And then the how to say the building plot should be a little bit more regular. Just rectangle would be the best. Don't use those have a very weird shape of the building plot, because that maybe cause some problem for the EvoMass when you to cutting the boundary. And if you already have some project when you in your undergraduate or master program, it will be good to use this project, because you can try to run the optimization for this project, and then to do the design again to compare the performance to your previous design and the design you conduct based on using the EvoMass. Or you can also try to find some design that is well known or famous for the green or the low energy or the passive strategy design, and then you can see how the EvoMass can evolve the design for the same design condition, and to compare how difference between the design used or without using the EvoMass. So I guess that's it. And here you are open to ask any question if you have.
Sorry, could you explain again about a penalty that you put in the algorithm? I didn't get when you put it, when you add the some amount of area, when we have a penalty. I didn't get that part.
Oh, the penalty section is actually, let me use another email, another computer to show you the thing. Sorry. This will be covered by tomorrow's section, but I just to I guess, oh, no, sorry. I guess you are asking the question about the penalty thing. So I guess. So you mean this part, right? The penalty part.
Yes, exactly. This session, this part, I didn't understand what happened in here. I know what is the penalty, and I know we add some to make those. When we run it, for example, when we have a point out of an area, we add a lot of distance to make algorithm it is wrong and make it back to the what it had to be. But in this part, I didn't get what you did.
Yes, actually, you say that in the algorithm, you have like a target Gauss area to help you to correct the design that to have a very close Gauss area to the target area. Yes, but actually, in some cases, even you activate this function, they can still generate some design that cannot fully satisfy the design, and sometimes you can also run the optimization without to try to constrain here if you want the design have more flexibility. But if when you whether or not you enable this function or not, I will try to recommend you to have this penalty function to ensure that all the design have satisfying Gauss area for the building design project, because we still because even for one thing, the hard constraint may not be can still have some probability that can be failed to create a satisfied design. And the second one is that this is just like an insurance that to prevent any invalid solution in the optimization algorithm. But if you're asking why, for this function, do you understand the meaning? This expression, do you understand the meaning, right?
So just we put a penalty when we have a large area that we do not want to have it in our alternative that EvoMass gave us.
Sorry, can you say it again, or can you type in the Zoom?
Yeah, I'm gonna type it. I'm gonna type it.
All right, and let me. We also have a question about the one fail goes red. It means that sometimes the EvoMass will help to will automatically detect some invalid solution parameter, but this function is actually not work very correctly every time. So, for example, for this column spacing, if you make a 4, and it means that it will have a notification of why this goes to red. But actually, the 4 is actually totally a valid number. If you want to hear 4, you can actually try to combine this to 5, and then you change to 4 is okay. So if sometimes goes to red, you can try to change this number. For example, if you set the floor number, you usually set the maximum number first. For example, you set the 15 and then you go to 15. But if you set the minimum number first, the design here will be go red. And then if you set the maximum number to 20, this will be still the red. So here you can just change to 19 and then go back to 20 is all right. So still while the parameters type, we have a penalty only when there is a large area. You mean the difference of the large area differences, right? Not the large area.
I mean, when we use a penalty, when, for example, we have a large area, I do not know, large, each floor have a different area. And I think we use penalty when it is, for example, over some number, and we try to avoid those, I'm not sure.
I guess, are you asking the question that, for example, we set a maximum number of the Gauss area? If the number above this area, this value, we will kill the design or just set this design.
Yeah, exactly.
Yes, this is called how to say, it's called a hard constraint. It means that any invalid design, we will just give them a very low or very poor fitness score. For example, you set the design has have a target area like 1,000 square meter, and then there have a design have a 1,001, and then you think this one is you will use a hard constraint to directly make this design very poor in the fitness. But I will not recommend you to do that, because you have to know that the mechanism of the evolutionary optimization is that even the 1,001 design do not satisfy your need. But if the 1,001 design have a very good performance, maybe in the next generation, he will be evolved a little bit to the direction you want, and then they will go to 1,000, and then they will still have a very good performance, because they the parent, the 1,001 parent have a very good performance. So in most cases, their offspring, their children will also have a very good performance, but they can satisfy your cross area constraint. This is the reason why we try to use soft constraint rather than the hard constraint to kill all the invalid design. So if you kill all invalid design, you will just in the beginning of the optimization process, you can only leave some maybe poor design can satisfy the constraint you set. But for the very good design, maybe just a little bit violate the constraint your set, they will be killed and disappear in the population. This will be a very big loss for the whole optimization process. So this is the reason why we try to use soft constraint instead of using a hard constraint.
So you think it is somehow it is narrow our option when we use this way, but
yes.
But maybe in this way we can control it more. I'm not sure.
But yes, there have many different types of the constraint you can use. I don't say that a hard constraint you cannot use. You can still use for some, but usually, for example, when we use this type of the thing, we don't use like this type of the. For example, in the yesterday's presentation, we used a lot of soft constraint. We didn't use any hard constraint to make the optimization to exclude the good solution. We just try to let the optimization or the evolutionary algorithm to understand how the design should be evolved. Because you use the soft constraint just like some kind of the approach to lead or guide the optimization process to find the desirable solution. But if you use hard constraint, usually it will make the optimization algorithm difficult to understand which one is have a good performance, because you kill too many potential or the possibility at the beginning of the optimization. So I never use hard constraint, and also I get some reviewers say that why you don't use hard constraint in the evolutionary algorithm. But I think maybe they just don't understand the negative impact of the hard constraint on the optimization part. Actually, for myself, I can't to imagine any situation you should use a hard constraint, because this usually is not the best way to combine with the evolutionary algorithm. But I can also show you, I'm still sharing my screen, right? Usually we will try to combine the soft constraint with some kinds of the, some kind of what? Yes, we usually have like in the machine learning, have a sigmoid function, and we can also use the grasshopper to create a very similar one, just like this one. Here is like a sigmoid function, which means that if we say the one is the thing we like, we usually can tolerate the design have a very small difference to the one we set. The one is the how to say is the like the standard or the point we want to reach. But when you try to drag this one, so we just just tolerate the design in this area. But when the design goes to a little bit more difference, their performance or the fitness will be decreased repeatedly, which means that this design will be repeatedly killed or excluded in the optimization process. So do I answer your question?
Yeah, sure. I had to experience myself as well to understand it deeply. But yeah, that was
and tomorrow I will also talk about the example, maybe a little bit more about the example I presented yesterday in the conference, and you can see how this short constraint to help the evolutionary algorithm to find the desirable solution.
Yeah, that was awesome. Thank you.
Oh, you're welcome. So, any other questions about this section? If no, we are good. We are over time for almost an hour. It's a very tight. I guess tomorrow may be a little bit shorter. We can make the section close on time, but today is a little bit long. And if we don't have any questions, I think I want to call it a night. And then if we still have anything to want to share or want to ask, we can post it in the Slack space. And okay, I guess so. If nothing, I guess there's something. Okay, all right. So I will terminate the Zoom meeting, and then we will see you guys all tomorrow. Goodbye.
Goodbye.
Bye bye. See you. Bye.